Welcome to the live coding session on behavioral modeling. In this session, I will discuss some examples like how to use the forever loop or how to use the for loop. I'm not discussing any design examples like decoder, multiplexer or counter because we have already seen decoder, multiplexer and counters using data flow modeling and gate level modeling many times, right? So in this session, I want to try something new. I want to show you what is the non-synthesizable delay that we have used so far, right? We already proved that it is a non-synthesizable delay, but I want to show why it is non-synthesizable delay and how the output will look like if you use this kind of delay, whether it is really giving the functionality that you are intended or not. I want to show in one example, and then in other example, we will answer this question. We all have seen so many times whether the for loop is synthesizable in Verilog or not, right? This question. We'll try to answer that question by our own approach. We'll try to explore the tool and then we'll see whether really the for loop is synthesizable or not in Verilog. So let's begin the live coding session. Create a project. I'm creating in the first project, I will explain the forever loop. So I'm creating a project called forever loop. I will design a clock generator using forever loop that I already discussed in theory. And I will use a delay element, right? But we'll see whether the delay is really synthesizable or not. So let's select the jetboard. So I want a clock output, which is a register of my clock, right? To create a clock using only initial statement, not always block. Initial, begin, my clock is equals to 1 tick binary 0, and forever after every 5 nanoseconds delay, my clock is equals to negation of my clock. Right, there is no error. Let's save this and run the simulation. We'll be able to see the clock signal. See, the clock is generated, right? At 0 nanoseconds it will be 0, and up to 5 nanoseconds it will be 0. At after 5 nanoseconds it will trip from 0 to 1. It will stay 1 for 10 nanoseconds. After 10 nanoseconds it will trip to 0 again. Like this, the clock will be generated, right? So this is just a RTL level simulation. Let's synthesize this and then we'll do the synthesized design simulation, post synthesis simulation. Till now we are only doing the RTL level simulation, but now we'll do post synthesis as well as post implementation simulations also. So how to do that? You click here, run simulation. Once the synthesis and implementation are complete, you'll get these enabled. You can run post synthesis functional simulation as well as timing simulation. I will explain what is timing simulation in the next example. And we can run post implementation functional simulation and timing simulation. Synthesis is successful, so we'll run the implementation in the background and we'll see the post synthesis simulation. So the implementation is running background. So let's run the post synthesis functional simulation. Remember, the synthesis is successful, right? It hasn't given any errors or warnings. So it has shown the synthesis is successful. Now let's see. There is no clock signal, only the clock is always high. Even if I run for 40 microseconds or any amount of time, still the clock is 1. There is no clock kind of output because the delay element is not synthesizable. Right? This is post synthesis simulation. If you want to check the behavioral simulation, you can check like this. You can do the tab shifting. This is behavioral simulation. In the behavioral simulation, you can see the clock is getting generated because RTL level the delay is synthesizable, but in the once the synthesis is done, then the delay element, it will ignore the delay element. Okay, So that's why we have to avoid these kind of statements in our code. We have to write our own delays like we have defined using clock divider circuit in the previous session, right? So this is what I want to show in this example, where the post synthesis, even if you do the post implementation also, the implementation we did, right? In the implementation also there is no error. You can see the schematic also, it is generating the schematic of implement a synthesized design as well as implemented design, right? But still it is not giving any delay. This is the synthesized design schematic. Now I'm opening the implemented design schematic, and if you see the RTL schematic also, you can see. So this is the RTL schematic. The RTL schematic. So the schematic is same in all the three cases, but if you run the simulation in synthesis, it is failing, right? It is not giving a clock kind of signal, but in RTL it is giving the output. So that is why you have to believe the post synthesis and post implementation simulations, but not the RTL level simulations, because the post synthesis and post implementation simulations are the real outputs of your code. Okay, and I want to discuss one important thing here. We are always seeing this time scale, right? What is this time scale? Whatever the delay that you are giving here, it will be in multiples of this time scale. Let's say I have given 5 as my delay, 5 time units delay. So the time unit here is 1 nanosecond. So this is the time unit, and this 1 picosecond is precision. Inside the 1 nanosecond time unit, you have 1 picosecond of precision. So it will be like the 1 nanosecond window is divided into 1000 blocks, because 1 picosecond is 1000 times of 1 nanosecond. 1 nanosecond is 1000 times of 1 picosecond, right? So the entire 1 nanosecond block will be divided 1000 times. So this is precision and this is time scale. So that is why our simulation, if you see the simulation result, I'm showing the simulation result. You see it is in time scale of nanoseconds. I have given only 5 as a time unit, but it has converted into nanoseconds. After 5 nanoseconds, it is going to 1. Again, after 10 nanoseconds, it is going to 0. If you want to make it microseconds, you can simply change it to microsecond. Then your output will also be converted into microsecond time scale. Okay. So let's create one more example where we'll explain the for loop. Whether the for loop is really synthesizable or not, we'll see. So I'm creating a new project to understand the for loop understanding. So I'm creating a project of for loop, creating a RTL code for loop, same jetboard I'm using. We like to close, yes. Let's start writing the code. We'll use the same example that we have discussed in the theory, like I have a state bus. In that state bus, I want to assign alternative zeros and ones, right? So my output is a output. See, I'm both declaring the ports as well as declaring the variable of the port also. Output is a register called state, which is a 32-bit register. So 31 down to 0. Okay. Inside this initial begin, I'm writing two for loops. I need an integer, right? So I'm calling an integer I. I can either initialize integer here or I will initialize integer in the for loop. For I'll write for I is equals to 0, I less than 32, I is equals to I plus 1. Okay. Inside this, what I want to write, I want my state of I is equals to 0. So I want odd numbers, right? So I have to increment by 2. Initial begin for and one more for. I will start with I is equals to 1 and I less than 32 and I is equals to I plus 2. Now in this also I am assigning state of I is equals to 1. So these will be counted from 0 to 4 like that, and this will be counted from 1, 3, 5 like that. Let's see the simulated result. We'll change this radix to unsigned decimal so that it will be easy for us. This will be binary. See, this is what we intended, right? The I is going from 0 to 32. After 32, when I becomes 33, it has stopped counting, incrementing. Even if you run it for any amount of time period, it will stay up to 33 only, right? After 33, it will end the loop. And whatever the state we have assigning, the 0th bit will be 0, 1, 0, 1, 0, 1, 0, 1, like this alternative 0 ones we have assigned. So our for loop is running, RTL is running properly. So let's create a synthesis. Now let's run synthesis first. We can see the elaborated design also meanwhile. So this is how it connected. Some of the nets it is connected to VDD and some of the nets it is connected to 0, right? Synthesis is done. We'll run the implementation in the background. So this is my output. So what I did, some of the outputs are connected to 1 and some of them are connected to 0. Now let's run the post synthesis functional simulation. See, now after synthesis we don't have I. Why? Because I is not a IO port. After synthesis and implementation you will have only IO ports will be displayed here. But in the case of RTL it will display all the signals that are available in the code, right? You have seen I is also displaying here. But after synthesis it will only display the IOs, what are the input output ports that you are declared in your module. So if you convert it into binary, you can see it is synthesizable because it is giving the output as intended. So the for loop is synthesizable. We can conclude that by this observation. We can even see the synthesized schematic. So this is the synthesized schematic. So it has connected some of the nodes to ground, right? 0th node to directly ground and 1 to VDD. Ground, VDD. Here VDD means logic high. This is logic high. This is logic 0. So it is synthesizable. It is creating a synthesizable design schematic as well. It is using just buffers and it has created whatever the operation that we want. Right? We can even see the implemented design as well, implemented schematic as well. See, implemented design is even compact. It has connected all the even values to ground, all the odd values to VDD. Right? So now let's explore more inside this for loop. What I thought is, because the amount of for loops, the amount of counts, it is counting up to 32, right, is small. That is why it is synthesizable. Let's say we'll count it for 1024 times. It is like 2 power of 5 into 2 power of 10, 2 power of 15 times. Let's see what happens. Let's see whether it is synthesizable or not. So first we'll run the RTL level simulation. We'll verify the output. Whenever it gives this kind of error, just close the already existing simulations. See, still the count is incremented as intended, right? Count is incremented for 2 power of 15 times plus 1 and my output is also correct, right? So let's do the synthesis. We'll see whether it is able to synthesize this much big for loop or not. So synthesis is done. We'll run the synthesis design functional simulation. Now see, the output is not synthesizable. It is giving 0. Let's see the schematic of the synthesis design. So it has connected all the outputs to 0, right? Now let's explore more in this content. Like instead of giving this much big for loop, so what we concluded from this observation, if the number of repeating loops are less, then it is easily synthesizable. If the number of loops is more, then tool will not able to synthesize the for loop, right? That is one hypothesis we made. Let's explore more. I want to create one more output like this output with some variable called a. Okay, it is also 32-bit output a, and I want to create one input which will control my for loop. Here we are not controlling the for loop with any variable. You can see we are only controlling the for loop with numbers. But let's say I want to control my for loop with some variables. So I am defining a 32-bit input variable like this. I am defining a variable called val, which is a 32-bit input. So I want to control my for loop with respect to this variable, not just by giving the number. Okay. Before that, I want to create one output for this register A. So for that, I am creating a temporary A, and I want to assign my A to this temporary A. So what I am doing is I am using a data flow statement, assign statement, which will assign the value of temporary A to output A. As you can see, I am mixing both data flow statements as well as these behavioral statements. All the initial, begin, for, these are all behavioral statements. I am using both behavioral statements as well as this data flow statement called assign in the same module. You can do that. That won't give you any syntactical error or any functionality error. Earlier, we don't have any variable dependency, so we have given the for loops inside the initial block. But we have now, we want to create a input variable dependency. So I am writing an always block. Always at the rate, I want to see if there is any change in the input variables, any input variables. That's why I have given asterisk. So it will monitor if there is any input variable changing, then it will execute all the following steps, right? So always at the rate asterisk, I want to begin with my temporary A is equals to 0. Okay. Here, instead of for I is equals to 0 to I less than 32, I want to give the input variable dependency. So let's say I want to multiply my for loop. I want to run my for loop up to 32 times of val of second. So second bit value, it should multiply, whether if it is 0, then it should not run. If it is 1, then it should run for 32 times, right? So I want to do this input variable dependency using for inside the for loop. Let's see what happens. Let's run the simulation. I think it will give the same error. We have to close the existing process. Now run the simulation again. Now see, the state is not assigned. Earlier case, the state is directly assigned because it is not depending on any inputs. Unless and until I give some input, the state will not assign any value. So I am giving some inputs, like I will use the force constant of inputs. Force constant. Let's say 1, 2, 3, 4, some hexadecimal value, and then I will run it for 40 nanoseconds. Let's say Now see, once I gave the value, let's convert this into binary. So since 0, 1, 2, the second bit of my value is 1, what happened? The second bit of value is 1, so that's why this is counting up to 32 times. That is why the state is assigning as intended. Right? The state output is correct as we expected. Right? 0, 1, 0, 1, 0, 1, alternative 0 ones. And my A output, you see what is happening with A output? It is incremented by 2 because I have defined always if there is any change, it is counting with, it is assigning 0 and then it will increment once it went inside the for loop. So let's define this outside, right? Only initially we'll define my temporary A is equals to 0. Okay. Before running this code, we'll see some other things here. Like if I change the value instead of 1, 2, 3, 4, I want my value should be 0, let's say. So what happens? If the value is 0, then it is not incrementing. See, the I is not incrementing, it is still at 21 only, right? Okay, let's run this again, and initially we'll give I value is 0, then we'll see whether the state is correct or not. Here the state is already correct, so the same state it is maintaining, right? But you can see the count is not incrementing because my value is 0. Okay, so I have made this change also. I kept temporary A outside in the initial block. Let's save this and run the code again. Now let's give a value of 0. Now see, the state is not getting assigned because the for loop is not entering. This for loop is not entering. Even though this for loop is entering, this for loop is not entering, right? That's why it is X, right? One of the things are X and one of the things are ones because one of the for loop it is entering. It is not having any dependency from my value. And this for loop is having dependency of value. That's why this for loop is not entering. Okay. And since we haven't used begin and end, this temporary variable is not inside this for loop. So that is why my temporary variable is already assigned without any problem with that for loop, right? So we'll write this inside begin and end. So this is how you need to debug your code. You have to explore the tool as much as possible. You will create some new difficulties to the tool and then you'll try to solve that. See, I am progressively going to my actual output. So I'm identifying what is the problem and I'm correcting them. So now this is in begin and end. So all these two statements will be dependent on for loop. Let's see what happens. Now let's see. Earlier we saw A is equals to 2, right? But now A is equals to 0 because it has not entered into this for loop, right? Now if I give my value is equals to 0 initially, okay. See, the state is not changing as well as my A is also not incrementing, right? And my temporary A will also not increment because temporary A is equals to A. We have assigned like that. Now I will give a value of 2 because I want my 0, 1, 2, not 2, 3, 0, 1, 2. Fourth bit 4 should be there, right? Then only the second bit 0, 1, 2, second bit will be 1. So yeah, now let's see what is happening. Since the second bit of the value 0, 1, 2, the second bit of value is 1. Now it is entering into the for loop and it is giving proper output. And it's binary, and this a is also incremented whatever we intended. It is incremented up to 32 because this loop will be executed 16 times. 16 times of 2 will be 32. Every time it will increment 2, 2, 2. So 0 plus 2 plus 4 plus like that, it will increment 16 times. Right? Because this is I plus 2, this loop will be executed only 16 times. So my A is 32. So our output is correct. Now let's do the synthesis and see whether the synthesized output is correct or not. You should not believe whatever the tool is giving. You should always question the tool whether it is true or not. You should go to your design and check whether it is correct or not. Why the output is becoming 32? Because I have given a plus 2. If I give a plus 3, then it will increment 16 into 3. That will be your output. Right? Now the synthesis is done. We'll run the implementation in the background and we'll see the synthesized output. Now see, after doing synthesis, it has created a lot of temporary resistors, right? Earlier it was not the case. So this is our input. We have to assign this input. Let's bring it top. Okay. Now again I am assigning my input. Let's say 4. I want to see the output directly. Now let's see. A is not decoding, but state is decoding properly, right? State output is correct. We'll see. State output is correct irrespective of the value, right? You can see even though if I am not giving any value, the state output is correct. How? If you see the synthesized design, then you can see the synthesized design is very big, right? In the synthesized design, the state outputs, it is already assigning ones and zeros directly without any dependency on input, right? That is why your state output, you see the simulation result, it was already ones and zeros irrespective of the value of input. Even if you give value of 0, it will be still correct output, right? But why A is not happening? See, it is still all access and only one of the bit is 0. That means only this is executing, but this is not executing, which is not synthesizable. You can see when you give input dependency, then your for loop becomes unsynthesizable. So these are the conclusions you can make. Whether the for loop is synthesizable or not, it depends on how you use the for loop. If you have smaller for loop with defined number of output stages, then it is synthesizable even if you have combinational statements inside this. But if you have for loop with some input dependencies, then it is not synthesizable because tool cannot recognize what is the value of 2 until you will apply from outside. So it cannot create the circuit. Once the value of this is available, then only it will assume okay this is 1, then accordingly it will create the circuit. But since it is an unknown thing, it is unable to synthesize this for loop. So this is the conclusions you can make by doing all this experiment. Okay. Now I want to explain some interesting feature like what is the post behavioral functional simulation and what is the post synthesis timing simulation. What is the difference between these two? I mean, why do we have different kind of simulation? What is functional simulation and what is timing simulation? Okay. So for that, First of all, I want to make this as a synthesizable output, so I'm bringing this here. Okay, and I want to have this temporary variable not just increment 2 or any constant number. I want to have it dependency on input. Okay, value of I, let's say. So let's save this. So what is the functionality here? The temporary A should increment based on the odd position values. The number of odd position values, it should count number of odd position ones, right? Because when I is equals to odd value, either 0, odd means I was talking first value, third value, fifth value, like that. In that cases, what is the value of inputs? It will increment, it will count. Okay, so let's do the simulation first, RTL simulation. So let's give an input, let's say 4. So what is my A? A is equals to 1. Why? Because 0, 1, in the second position there is only 1, 1. Let's say if I create one more 1 here, let's say if my value is 5, so my output is 2, because there are two ones in the odd positions, first position and third position. Similarly, if you give some number like constant, any number, let's say 1, 2, 3, 4. In that case, how many ones are there in the odd position? 1, 2, this is not odd position, and this is odd position, only 3. So my A is 3. So A is working as intended. It is counting the odd position ones. Okay. Now let's do the synthesis of this. We'll see the synthesized output, functional output, as well as timing output. Then we'll decide what is the difference between synthesized functional output and timing output. Synthesis is done. Now let's run the post synthesis functional simulation first. Now let's give same input. My value is equals to, my value is equals to 4, let's say. Then my output should be equals to 1, right? A should be 1. So I'm running. Now see, the A is 1, right? If I change the output to 5, input to 5, then A should be 2. So now the for loop is synthesizable, right? It is giving the output as intended. A is 2. Okay, this is functional simulation. Now let's run timing simulation, post synthesis timing simulation. Now let's give the same inputs. First we'll give input 4. Now let's see the timing. You see they are executing at different times. Why? Because the path delay of all of these is different. If you do the synthesis, synthesis means actual implementation of your design. See, because in functional, I can switch the tabs like this. I'm going to the functional simulation and I'm checking at what time period my A is becoming 1, right? Exactly at the same time period, I'm changing the input. See, I'm changing the input from 0 to 4 at time 1000 picoseconds. At the same time period, my A is also changing. There is no delay, anything, right? But in case of timing simulation, you can see it is delayed by 6 nanoseconds, right? I change my A. Let's bring the value to the top, we can see clearly. See, I am changing my value here at 1000 nanosecond, but it is changing its value at 1000.6 nanoseconds. So there is a delay of 6 nanoseconds. Why the delay is existing? You can see the schematic or implemented design, then you will understand why there is a delay. See, the output A is passing from all these nets, should cross all these nets all the way from here, right? From here to here. You can see the implemented schematic design as well. It has lot of nets involved. That's why it is having different delays. Okay, you can see this from schematic as well, implemented design as well. Same thing if you do the post implemented timing simulation and post implemented function simulation, you can able to see there is mismatch in timing. That is why it is always advisable to give the timing constraint to your design to ensure that your design is meeting the timing requirement. If you don't consider this delay, if this signal is going as input to some other block, maybe that block is expecting the output at 1000 nanosecond, but this block is giving it 1006 nanosecond. So there is a mismatch of inputs. So your entire design output may be corrupted. So these things we will see in the next module where we define setup time, hold time, and how to give the timing constraints. There you will understand better what is the importance of the timing in any digital design. So this is a post implementation design. We'll run the same input. The post implemented design will also have some delay. So even though I'm changing at 1000 nanosecond, my post implemented design is changing at 1010 nanosecond. You can see the synthesis is giving only 6 nanosecond delay, but implementation is giving 10 nanoseconds delay. Why there is difference between synthesis and implementation? Because synthesis will only convert your RTL to gate level netlist, but implementation will actually implement on the JET board. So the implemented result is your final result of your design. So whatever the timing constraints you have to meet with implemented design. So you have to assume that your design, whatever design you did, this is having a 10 nanoseconds of delay. So after 10 nanosecond delay only, you will get the proper outputs. Until then, you will get unknown outputs like this 00x. So after 10 nanoseconds only, you will get the exact outputs of your design. So this is the main difference between functional simulation and timing simulation. You should not believe the functional simulation, you should always believe the timing simulation, because that is the true output of your design. Okay. With this, I am concluding the behavioral modeling as well. In the next session, we will see some advanced topics in Verilog, and we will see some topics like what is switch level modeling and all in the next session.